Hello and welcome to the eighth question answer session. In this session, we have got two questions to answer. The first one is about the interpretation of NMR spectra, and the second is about reaction mechanism. So let's begin. Right, so the first question has been asked by Shima, and she asked, what is a good software or an appropriate software for interpretation of NMR spectra? So you can play with your NMR spectra using Mastronova software as well as the Topspin NMR software. I've already uploaded tutorials on Mastronova software. You can see the link up there. And in near future, I'm going to upload video on the tutorial video on Topspin as well. So you can go and watch the video on Mastronova, and if you still have any questions, feel free to ask. The second question has been asked by Fahad, and he has sent a question about the addition of HBr to a conjugated diene. So we have a situation, a conjugated diene, and we are going to add HBr onto that molecule. We have four options and we have to select the correct one. So I'll take you to the screen and help you understand the question and answer it. Okay, so the question being asked here is that we have this diene, which is not a symmetrical diene, and it is treated with HBr. And so what would be the product? Of course, the product would be an addition product in which HBr would be added across the double bond here. Now, the question here is that we do not have a simple alkene, but in fact we have a conjugated diene system. And whenever we have such a system, addition of HBr could yield two different products, a 1,2 addition product or a 1,4 addition product. Let me give you an example here with a simple 1,3-butadiene. If you add HBr across this double bond or this diene, so you might expect this product in which H is attached at the terminal carbon, bromine is attached here, so it's a 1,2 addition product, or you may expect the formation of this product, which is a 1,4 addition product. So let's apply this concept to this molecule here, and this is not a simple 1,3-butadiene. In fact, it's a substituted 1,3-butadiene, and we have a CH3 group attached at position 2. Now, HBr is an acid, so it will protonate this double bond. So it can protonate the double bond on the left and it can protonate the double bond on the right as well. And we have 4 carbons to which this hydrogen could be attached. And whenever this happens, we will have a carbocation generated. So when a double bond, a pi bond is protonated, it generates a carbocation on one of the carbon atoms, on the adjacent carbon atom to which the hydrogen is attached. So let's see what carbocations we can have. So if this hydrogen gets attached to carbon number 1, let me label them for you. So if it gets attached to carbon number 1, we will have a carbocation at carbon number 2. So hydrogen comes here, a carbocation is here. If the hydrogen is taken by carbon number 2, then we will have a carbocation at carbon number 1. Similarly, if the hydrogen is taken up by, or it gets attached to carbon number 3, then we have a carbocation at carbon number 4, and if it gets attached to carbon number 4, then we will have a carbocation at carbon number 3. So we can have 4 different carbocations, and you already know that the formation of the most stable carbocation out of these would be more feasible. So that is the rate determining step, the slowest step, the formation of this carbocation. So you can see that we have a tertiary carbocation here, a primary carbocation here, a primary carbocation here, and a secondary carbocation here, which of course is also resonance stabilized. So when we have a secondary and a tertiary carbocation, we can not have a primary carbocation. So the possibility of the formation of these two carbocations would be the least, almost zero, because of the fact that these are primary and also they are not conjugated. While if you look at this tertiary carbocation here, it is involved in resonance with this pi bond. Similarly, this secondary carbocation is involved in resonance with this double bond or this pi bond. So both of them are allelic carbocations, but this tertiary carbocation, this tertiary allelic carbocation has more advantage in being tertiary as well as being an allelic carbocation, so it is more stabilized as compared to this secondary allelic carbocation. So the first riddle is solved. We will have this tertiary carbocation, which is of course resonance stabilized. Now, the second step, which is the fastest step in this reaction, that would be the attack of the bromide ion on the carbocation. Now it has two options, whether to go for the tertiary carbocation side, the tertiary carbon, or whether to go for this terminal carbon. So you can see that it will experience some hindrance when it is going for the tertiary carbon, but it won't experience any hindrance when it is going for this terminal carbon number 4, as seen here in the original structure. But still, if you take that out of the equation, we can still have two types of bromides. So either this is formed or this product is formed. So out of these two, now which one is the most suitable or probable product? You can see in the product on the left, the double bond is terminal. It's a mono-substituted alkene, while the one on the right is a tri-substituted alkene. And you know that the more the double bond or the pi bond is substituted, the more stable it is. So from this discussion, it seems that this would be the most probable or the only product formed in this reaction. So you have 4 options. I'm sure that one of them would be this product, and so that would be the major product of this reaction. Right, so these were the 2 questions asked for this session. I hope you have got answers to your question. For rest of the viewers, do send your questions on the email address given below. I'll be waiting for your questions. See you next Friday with new questions and new knowledge. Thank you so much.